Hi, welcome today. I did want to mention a couple things. So I would prefer, if you do have any questions, to email me through Canvas. I will get to those first. So some of you have been emailing me through my normal account. So please email through Canvas is the preferred method, because I will address those first. If you have any grading issues on quiz or homework, check with the TAs first. So in Canvas, you can select all the TAs if you don't know which one's the grader. And so just select all of them and send them a message. And then if there still seems to be an issue, then reach out to me. Do note that there's extra credit for any errors, so spotting errors. So these can be found under the my courses. So under the discussion section, there's the spotting errors. So if you have any error, do make sure to put a screenshot of what the error is, unless it's during a quiz day. On the quiz day, just put the question, what you have as far as the error, that it said this, and this is actually what was coming out. I don't know why my internet's not working. In practice problems, ignore the due date if it has one on there. Those are available for extra credit throughout the whole semester. Okay? Any questions about anything up to this point? Okay. Also, remember, note that Thursday night, you will have a homework and assignments are due, and then Friday, so this is by Thursday night, and then Friday only, the quiz will be open just on Friday only. So I had some students that reached out and were confused about that, so I did want to make sure, again, another announcement. Friday only that day, 12 a.m. to 12 p.m. So full day, whatever. If you want to wake up early, you stay up late the night before, whatever you want to do, or do it sometime throughout that day. But it will be only available on the one day. Okay. Anything else? Any questions about material that we've covered so far? Okay. So last time we went through. Talked about that RoboBee, if you remember the RoboBee with the strain gauges on it, which are kind of cool. So those resistors will change. So we talked about the whetstone bridge, which is the circuit that's used to detect changes between different ones of those strain gauges. Then we talked about the superposition, and we got through one example, and then we're going to pick up again with this second example of this one. So we want to solve this one. So we're going to first leave the voltage source, and when we turn off the current source, what happens to it? Okay, great. Open, yes. So our new circuit, you need to redraw it, and our new circuit will look like this. It will have an open here. We are solving for IR3. And so work with your neighbor. If you are sitting again with a new neighbor, please introduce yourself. Otherwise, Try to find IR3 for when you just have the voltage source in there. Put it up here.
Voltage source divided by parallel, and then two the first one that we R2 plus V divided by R plus 6. It would not be really. Like a step. So does that have any I guess that's like
I like this help. I like this help. How do we even do this? So let's start there with the help. How can I even do this? Okay, so if you don't even know where to start, Anybody want to say where did you start for those that were able to get somewhere with this?
Find the resistance equivalent.
Okay, so you could find the equivalent resistances and redraw the circuit with those. I'm just going to copy it over and then do it. Okay. So doing that, the equivalent, I can't talk today, I guess. The equivalent would be in the branch with this one. What's this going to be? Okay, and how did you get that?
2 plus 3.
Okay, so you notice that they're in series. So you have an ordinary node in the yellow one. Said I can't talk today, but this is an ordinary node. So ordinary, extraordinary, and extraordinary. So you can combine the ordinary one together for one resistor. So that would be one resistor of a value of 5K. Don't forget the K. Units make a difference. So then you would have IR3 going through that one. Okay, so you've used combination. You can't simplify it anymore because they're extraordinary nodes. From that, what do you notice? They're parallel, correct? So that means that you're going to have that the 12 volts is the same voltage across both. So remember, parallel, you have same voltages across each of the parallel branches. So if I ground this side, this node here, everywhere on that node, which is also going to be this one, is going to be 12 volts. So then what other techniques do I have?
Adding reciprocals?
A which?
Adding reciprocals to equivalent?
So I could combine those, but my goal is to find IR3. If I combine them into one, I've simplified the circuit, but that also doesn't give me the information I need for IR3, which is in only that branch with the 5K ohm. So I could simplify it again to get just one current and find the current would be here. So one thing I like to ask when I'm trying to solve a problem is, what am I trying to find? IR3 in this case. Can I write an equation for IR3? So I want to go through the techniques to try to find an equation that has IR3 in it. So that would be how I'm trying to approach a problem. So what is my unknown? So I ask those questions. What's my unknown? And can I write an equation with it in it? So to write an equation, I have three techniques: KVL, KCL, and Ohm's law. So those are the three I can go through to say, does this help me get an equation with that IR3 in it? So then I can do, is a KVL going to help me here? If I take a KVL, I'm going to want to do a branch. It won't let me write that. A branch or a loop with the 5K in it. Also, I would want to take take a loop with the most known values in it. And in that case, what's known is the 12 volts here. So can I take a loop with the IR3 and that 12 volt? Yep, I can do that. So let me take one through there. I'm going to start at my 0 point, go through here. I need to label the plus and minus on the IR3. And so this is going to give me a plus here and a plus here. So plus 12 plus IR3 5K equals 0. And I can solve this for IR3, which will be a negative 12 over 5K. And that would be an answer right there. If that didn't yield an answer and I had an equation with more unknowns in it, I would then need to write an equation for those unknowns using the same thing. Look at KVL, KCL, Ohm's law. What if I didn't start with KVL starting with it? Could I do a KCL here? I could have started with KCL. Since I put my ground over on the left side, I could do a KCL here. I would just need to label a current here. So I could say plus to minus there. And I would need to label I'll call it IS, a current there. So coming in would be IS and IR3. And then going out, I'll call that I1, would be I1. So here I have unknowns of I1 and IS. So I would need to write equations for them. So I can't do any more KCL, but I could go back and look at KVL and Ohm's law for those. Ohm's law, if I know the voltage across a resistance, then I can do a current of that one. So I know the voltage on the right side, and I know ground, 0 volts is on the left side. So here's my KCL, my KVL, and then Ohm's law. We're going to have a plus and the minus are the same for the VS and the R1. So I know that I1 is going to be VS, which is 12 over 1K, and it's going to be positive because the polarities are the same. So here I see that the polarities are the same on the right side, and then they're the same on the left, so I have a positive IR. Yes?
I was wondering why you drew the plus on the left side for the R3 for the resistor.
For IR3?
For IR3, yeah.
Because the negative is always where the minus is. So I was following what was in the original drawing,
Okay,
and so that's why I labeled it as the plus minus there.
gotcha. So the current always goes from high to low voltage. And then,
Yeah.
but since the current is negative, it's really going in the other direction.
Correct. So that negative means like, oh, it's actually flowing the other way. Okay, so I went that way. If on this one, I also know across the 5K, but here I notice that those polarities are opposite the polarities in the VS source. So with this one, it would be a negative of the IR. So because these are opposite the source, IR3 is got to be that negative of the source 12 over 5K, which is the same as when we did the KVL. So you could use, in this case, you could use either methods. Does that make sense why it's negative? I think some of you are still getting some things wrong on that quiz. So do make sure you understand those polarities do make a difference. And it depends on what was labeled. So I think in one of the quiz questions, it asked for something like this, where it was a resistor and the labeling of a current. You had to note that the source was different than the label was for that current flow. And therefore, that's why it was negative. So current and voltages you can have be negative. That doesn't mean that their value is negative. It means that the polarity is either, for a battery, it means the polarity is opposite what the labeling was. And for a current, it means it's opposite what the label of the direction of the current is. So that's what the negatives mean for voltage and current. So make sure you're understanding that concept, especially as we're coming up on the first exam. Okay? All right, other questions on this one? Okay, so let's do the next step of this, which is to move to taking out the voltage source in this case and keeping in the current source. I'm also going to write this in milliamps just so it will be easier to write again. So this is a negative 2.4 milliamps. Okay. Go back to this one. Okay, so what happens when we put a source to 0? A voltage source, I mean. It's what? Thank you, yes, it is a wire. So this time we have a wire. So this is going to go here. What does this do? What do you notice when you put a wire there? It shorts, correct. So this is called a short. And it's going to short whatever's in parallel with it. So if we highlight everything between all of the elements, we see that this actually goes over here and is going to short which one? The 1 ohm or 1 kilo ohm. So ignore this, shorted. So now we have a current and then 2 branches. So this is still an extraordinary node here at the red. And I can label this again as my ground point over here. And we have 2 extraordinary nodes. And the same coloring on both the extraordinary nodes for the current source, the 3K and the 2K, so these are going to all be in parallel with each other. So same idea. What am I trying to find? Can I write an equation for IR3 again? I write the equation looking at the 3 laws that I know, KVL, KCL, and Ohm's law. Okay, try and solve this one for IR3 when you just have the current source in here.
So we're going to have
No, it just erases by hand. It's actually it's like an that can't be edited. But it's not really Well, someone's right now. It's better if not. I think that the deep dive.
Okay, so a step forward in that a lot of people were able to actually start to answer this one, which is good. So good job. It did look like there was a consensus there of 0.8 milliamps. So let's go through the solution here. So on this, some of you noted that this was a division of current. It had two branches that had resistors only in them. And they went, so the current goes in and then splits and goes through two different branches. So you could use a current divider here. So IR3 would be 2 milli, and then you could do 1 over 3K, 1 over 3K plus 1 over 2K, or you could write it as 2 milli times 2K, which would be the opposite branch over the summation of both those. If you don't see that it's a current divider, you would go back to the KVL, KCL, and Ohm's law. So with that, I would need to have currents labeled in each of these. I'm going to follow the direction of polarity of this one, so I'm just going to call it IR2, and I'm just going to keep the same polarities as what was labeled here, so I'll label that IR2. So going into this node, I have IR2, IR3, and going out would be 2 milliamps. And then I can take a loop. I'm going to actually go this direction. Do a different color. And I'm going to go around that direction, which is going to give me a minus here and a plus here. So I'll do the plus on this one. And I'm going to substitute in the IR for each of those voltage drops. So VR2 I know is the same polarity, IR2 times 2K. And I can label a VR3 across that, which is going to be IR3, 3K. And then as I do my loop, it's going to be a minus IR3 to 3K plus IR2 3K. And then I can substitute in one of these. I can say is minus 2 milli minus IR3. And then plug that in for IR3 here and get one unknown and one equation. And then solving this, I end up with the same equation. So I would have 2 milli. Whoops, where did I write this wrong? IR2 is 2K. 2K. So this is going to be then I missed something. Where did I go wrong? 2 milli times 2K. There we go. Would be 2 milli times 2K over 3K plus 2K. So that ends up being the same equation, and I get IR3 in this case is the 0.8 milliamps. All right, questions?
What was that last method you just showed?
So this was, I used here, this is a KCL here. And then these were Ohm's law. And then this one was KVL. So I used those three methods to solve for that one. All right, any other questions? Okay, so now I have the two solutions. And remember, for superposition, you find it for one source, you turn off all the other sources. And then at the end, we add them all up together. So this is the easy part, is we add up the solution 1 plus the solution 2 for total. So we had minus 2.4 milli first, so IR3 total minus 2.4 and then a 0.8 milli for a negative 1.6 milli, if I did my math right. All right, any questions? Okay. You guys good now with superposition? Okay. Next topic is Thevenin equivalence. So, continuing on with, well, I'm going to skip the Thevenin for now. We'll come back to that one. Okay, so a cell phone battery pack kind of looks like this. You have a component called a MOSFET and DC to DC power. It's called a buck boost power booster. You've got a fuse in there to hopefully go off before everything blows up. And then you have a whole bunch of different components in here, a temperature sensor, a current sensor. So it's becoming a smart battery, so that if you put in too much current, too much voltage, it gets too hot. You've seen probably on your phones, they actually automatically will turn off now, which is nice. So that smart battery system is kind of what you're seeing now in your cell phones. So it's detecting when the temperature is too hot and says, turn off everything, it's too hot, it needs to cool down. It usually sends a notice now too, which is nice. So how would we analyze something like this? It looks pretty complicated. And so can we just use something simpler to model this more complicated circuit, but still get the information out of it that we want? Typically, we want to know voltages and currents. So is there a way we can simplify this more complicated circuit and get just the current and the voltages out of it? So we have this block diagram now. Should I call it an iPhone? An iPhone in there. So our iPhone or phone system is now like modeled as this black box. And what we want out of it is to know like what kind of current, when we put on this voltage, I guess it would be going the other way, is this going to be drawing? So remember the battery, if you see it in this symbol form, that smaller line on the bottom is the negative side. So that's how you determine the plus and minus on that symbol for a battery. So we kind of want to know like how much current is this going to be drawing? And then overall, one of the other useful information is how much power is this consuming? So how would we determine power in this case? The power this consumes is going to be what? Say it a little louder. Correct. So current times voltage, and in this case, once we know what that current is, we could use it, and then it would be times the voltage set there of 4.8 volts. So that would determine how much power is this phone consuming. So pretty complicated circuit in there. We wouldn't have to analyze all the parts if just from an outside we just say, well, how much current goes into this? So now we want to know, like in here, how can we model all that complex circuitry by something that's simpler? And so we can maybe just put that model on there and then calculate just one current. That's much simpler than trying to analyze the whole thing. So what we come down to is what's called the Thevenin equivalent circuit. So if we can find a resistance and a voltage and use that as that model, then we have simplified the circuit. We know how to analyze a circuit like this. This is much simpler, just having a resistor and a voltage than all of those blocks that you saw beforehand. So we're going to learn the technique on how to make a more complicated circuit into those two components. And then that way we could just measure what, or determine what the current is, and then find something like the power of a system. So to find the Thevenin, what that means is that we want to find these two components. So we need to find an RTH and a VTH. So a couple things we notice here is that if we remove whatever other load is to this circuit that's modeled by this RTH and VTH, could we find RTH there? We would just simply need to find the pathway from the top point, which I'll call A, to B. And by doing that, if we shorted VTH, made that a wire, that would just literally be the pathway from A to B, which would be what we've done for our equivalent circuitry. So that's all you have to do to find RTH. So for RTH, we're going to short the source, or I'll say set 0 sources in the circuit. And that's going to be the same as shorting the VTH. And then find pathway from your A to B. And that equivalent resistance will be RTH. Does that make sense? I'm going to leave that there. Okay. Also removing the whatever load you have on the circuit. VTH, because there's no current that flows now, that voltage will be 0 because we have it open. And so if I measured just between A and B and found that voltage, this voltage here is going to be the same, VTH. So that means all I need to do is disconnect it from whatever circuit between A and B, find this voltage, VTH. And that's how we'll find VTH. We call it the open circuit voltage. Between A and B. And so these are things that we know how to do now. So when we determine where A and B is on the circuit, and then we're going to remove the sources and find the equivalent resistance pathway from A to B, that's going to be RTH. And then find that open circuit voltage between A and B, and that's going to be VTH. And then we'll have created this model that just has RTH and VTH, and we can easily find the current for whatever load we put on that circuit. Okay? So hopefully that makes sense, like the motivation behind this. And now let's look at this technique. So finding the Thevenin equivalent for this circuit. So we see RL, and it has to be told to you, like RL is the load here. So knowing that this is the load because I told you so, all we have to do is remove that. So step 1 is remove load. And label A to B by removing load. Some circuits you may get and they won't have a load on them and it will already be determined, here's your A and B location. In that case, you already know A and B. So once we know A and B, we want to find the pathway from A to B for our RTH. What else did we need to do for that? There was one other step before we just find the pathway. So we have to set the sources to 0. In this case, it's going to be a voltage source. So set Vs equals 0. Nice thing about iPad, I can just erase it. That's going to put a wire here. If this was a current source, again, and remember it opens up there. And now I'm going to find my pathway from the A side. Yes?
I was just wondering what the load means, like in context.
So a load is what it implies, a load to a circuit. So trying to think of a good example. So a stereo system, which hopefully all of you are familiar with. So you have your stereo system, and then your stereo system has all this electronics in it. Then you hook it up to a speaker, and the speaker gives you the load to that whole stereo system. In that case, the load would be your speaker.
So like it draws power out of it?
It draws the current and voltage out of it, yeah. Yeah, so that would be a good way to think about it. Is it something that you put onto a system that's going to load it down and draw that power out of it, draw the current out of it? Okay. All right, so what is the equivalent resistance between A and B here? Anyone? Okay, I'm not sure, so I'm going to highlight all of my nodes again. What do I notice there? The pathway between A and B. They're parallel, so my RTH is R1 in parallel with R2. So 1 over 40, 1 over 120. So 30 ohms is my RTH. Then I have to find VTH, And on VTH, I'm now going to find this voltage between A and B with it being open. So that means A to B. And typically, you're going to want to put B location as your ground. So that makes it easier then to find the other. You just have to find one side. So again, highlighting this, I've got all of that is going to be 0 volts. So I need to really just find the voltage here. So take a second and see about finding that voltage. So same idea, I need to find VOC or VTH there. So try and write an equation for that by using the 3 lots. Okay, a lot of you are very quick. Good job. All right, so one, I could notice that this is meeting the requirements for that voltage divider, and I'm trying to find the voltage across the R2. So it would be VOC, which is also your VTH, is going to be 20 times 120 over the summation of all them, 160. What was it? I forgot, 15 or 15. And so that gives you that 15. Wait, 120. Yeah. So that gives you the 15 volts. If I don't see that, that's okay. I can go back and say, like, okay, I want the voltage across here. And so I have one branch of current. So I'm going to label that I. Notice, remember, a floating wire, even though it's there, is not going to have current going through that one. So it's only one branch there. So current flows as one branch. And so plus to minus, and this is 0 on the bottom. So if I go around in this direction, I have a plus, minus, minus. And that equals 0. And then solving that, I get I is 20 over 160. And then I know that VOC is I times R2. So 20 times 120 R2 over 160, which is the same equation. So again, this polarity is going to be the same because the ground is on the bottom 0, so plus would be the A side, which is the same polarity, so I have a plus IR. If the current was going the opposite way, it would be a negative. Yes?
So to find the voltage, the TH, you don't take away the source. Just to find
Correct.
the resistance TH, you take the source away.
Correct.
Okay.
Yep. Okay, I had a question about this parallel form, and a student, I explained it a different way. So if you don't see automatically that there is a parallel between A and B, another way that you can do this is, again, it's highlighted this way because adding on the A and B are extraordinary nodes. So remember, when you add those in, they become extraordinary nodes. But that still may not make so much sense to people. So another way of looking at it is to look at the pathway. So looking at this pathway, if I start at A and I move through this to get back to B, I notice that there's a split here. A split means parallel. So I know that those two branches have to be in parallel. And then looking at the elements in those branch, I go through this one, which is going to be a plus series. And this one, R2, there's just R2 only. And then they join up together. And so that ends the branch elements that are in there. So that's, again, another way I can do that they're in parallel, is that whatever branch 1 would be in parallel with whatever's in branch 2. And that's due to the split. So split means parallel, going through an element means plus. I don't know if that helps. Yes.
So we set the sources, the voltage sources to 0 when we're finding the resistance?
Correct.
Okay.
So do memorize that. So this is only to find RTH. And that's basically, I'm removing the sources in the circuit and just finding the pathways. For the voltage VTH, you have to have sources in there to determine what that is. Does that make sense? Okay. Other questions? Okay, so this ends up being our resultant circuit. So say this is modeling a more complicated speaker circuit. I could put on a speaker here. And it would act as a load, RL. And I could model that component as, typically you model it as a resistance. And say it was a 10 ohm resistor. I could now find the current here. I'll call it IL as my load current. What is IL going to be? I heard somebody say it. 15. Correct. It's just going to be Ohm's law, which is 15 over all of the resistance, because there's only one branch here. So it would be 15 over 40. And that would be my IL. And I could determine how much current is going in there. So much simpler circuit than a whole bunch of complicated blocks that you have in a big diagram. Okay, so here's kind of a summary of the steps of finding that Thevenin equivalent. So choosing the polarity for VL, So typically I'll put plus on the top and minus on the bottom, but that's going to depend on where you also put your ground in your circuit. So I also like to label my ground as that negative side. And then you remove the load and calculate that open circuit voltage where the load used to be. That's going to be your VTH. You're going to zero all sources, replace the voltage sources with what? Wire, good job. And current sources with open or break, correct. And then you're going to compute the total resistance between the load terminals. Instead of compute, I'm going to put find pathway. Between the load terminals, which is A to B. That's going to be your Thevenin source resistance. And then you can redraw the Thevenin circuit, including those new values. And then you put the load on that redrawn circuit and then can calculate anything you want. The voltage across the load or the current through the load. All right, so this was the example of this. This isn't a super complicated circuit, but you can still see how it was reduced down to a simpler one. In this case, this is applying an RL of 60 ohms, but that can vary depending on what you put on the circuit. All right, so here's kind of an example of like, okay, well, what if RL is different values? So if it was 1 ohm, my voltage would be these values here. So lower resistance, I'm going to have lower voltage across it. Higher resistance, I'm going to have higher resistance. And then my milliamps, because of I is going to be the VTH over RTH plus RL. And your voltage across the load is going to be that I times the R load. And then my milliamps corresponds the other way. So I have, for the low resistance, I have a higher current, 483.871 milliamps. And then as I get to a higher resistance, I have lower current. All right, questions? Guys ready for some problem solving with your homework? Okay, so this is what you'll do for homework, is doing superposition and Thevenins. All right, any questions? Okay. All right, we'll see you guys on Thursday. Have a great day.